In this session, I am going to teach you context-free grammar. First of all, we see the learning objective. This is mainly to represent the syntax of high-level languages. Parser is used as a powerful tool in verifying the syntax of any high-level language. This is one of the application of finite automata. It makes the student to understand the context-free grammar and makes them to derive the string using leftmost derivation and rightmost derivation. While deriving the string, they have ambiguous grammar. So they will understand what is ambiguous grammar and thereby they remove the ambiguity. First of all, we'll see what is grammar. Grammar consists of 4 tuples V, T, P, S, where V is set of variables or non-terminals which can be expanded further. T is set of terminals which cannot be expanded further. P is set of productions or rules that represent the recursive definition of a language. Each production consists of a variable, production symbol, arrow, and a string of terminals and non-terminals. Left hand side of the production symbol is a variable and right hand side will be a combination of variable and strings. And S is the start symbol of this string. Next we will see context-free language. In context-free language, we have all the productions will be in the form of A tends to S, where A is the variable, S is the set of variables and terminals. Language of a grammar will be represented by L of G, which is equal to W, where W is a string which is derived from S, where S is the start symbol. W belongs to T, where T is a set of terminals. Next we will see the example for context-free language. Here we have considered the production S tends to A, S, B and lambda. We can derive the language of grammar, that is L of G is equal to A power N, B power N, where N is greater than or equal to 0. We can derive this using S tends to A power N, B power N for all N greater than or equal to 0. If L is equal to L of G, then we have language is said to be a context-free language. Next is the another example. Here we have 3 productions S tends to A, S, A, S tends to B, S, B, S tends to lambda. So we here in this example we derive the string A, B, B, A. So first we will start S tends to A, S, A. This S has to be replaced by B, S, B using the production 2. So it becomes A, B, S, B, A. Again this S has to be replaced by lambda, so it becomes A, B, B, A. Hence finally we derived it. If we have palindromes of even length, then we have grammar to be context-free grammar. Next we will see the derivations. Here we have considered 5 productions. Production 1, S tends to AB. Production 2, A tends to AAA. Production 3, A tends to lambda. Production 4, B tends to BB. Production 5, B tends to lambda. First we will derive the string AAB using leftmost derivation. Leftmost derivation means at each step we have to substitute the leftmost variable. So using production 1, S tends to S becomes AB. Using production 2, here we have A is the leftmost variable. It has to be replaced by using production 2. So it becomes AAAB. Here A is the leftmost variable again. So using production 3 it has to be replaced. So it becomes AAB. So here we have B is the leftmost variable. It has to be replaced by production 4. So it becomes AABB. Here B is the leftmost variable. It has to be replaced by production 5 lambda. That is it becomes AAB. Same string which can be derived using rightmost derivation. Rightmost derivation means we have to substitute the rightmost variable at each step. So S tends to AB is the first production. Here we have B as the rightmost variable. It has to be substituted using production 4 of 5. So we will substitute using production 4. So it becomes ABB. So using production 5 we substitute B. So it becomes AB. Again we have A is the rightmost variable. We have to substitute it by production 2. So it becomes AAAB. Here we have A as the rightmost variable. Now we have to substitute the production 3. So it becomes AAB. So the same string can be derived using both leftmost derivation and using rightmost derivation. Next we will see the derivation tree. Derivation tree is a pictorial representation of derivation process. These trees also called as syntax tree, parse tree or derivation tree. Here we have start symbol as the root node, variable are the interior nodes and terminals are the leaf node. Here we have considered the same protections. We have derived this string using leftmost derivation. For this we will see the derivation tree, where derivation tree is a pictorial representation of derivation process. So first here we have substituted the first production. So that is S tends to AB. So S yields AB. Again we have to substitute second production, that is A tends to AAA. So it yields AAAB. Next we have to substitute fourth production, that is B tends to BB. So at the leaf node we see we yield AAABB. Now we have to substitute third production, that is A tends to lambda. So we yield AA lambda BB, which is equal to AABB. Next we have to substitute B tends to lambda, that is fifth production. So we have at the leaf node we have AA lambda lambda B, so it becomes AAB. Hence we derived the string. This is derivation tree. We have leftmost derivation and rightmost derivation, both have the same derivation tree. Here we have this derivation tree for both the derivation. Next one is the grammar for mathematical expressions. Here we have considered the production E tends to E plus E, E star E, E enclosed within parenthesis and A, where A is a terminal, E is a variable. Here we have to derive the string A plus A star A plus A star A plus A using these productions. We have to evaluate using precedence. Here we have derived the string A plus A star A using derivation tree. That is, we have considered E tends to E plus E as the first production. That is, this E has to be replaced by A. Again, this E has to be replaced by E star E in order to get A star A. So, it becomes A plus A star E. Now, it becomes, again E has to be substituted by A. So, A plus A star A. The derivation tree for this leftmost derivation has been shown here, and we can have one more leftmost derivation for the same string. If we started from E tends to E star E, so we have to replace first E by E plus E. So we have E plus E star E. So now we have to substitute A for E. So A plus E star E, again A for E. So A plus A star E. Again if you substitute A for E, then it becomes A plus A star A. So this is one more derivation tree for the same string. Here we have two derivation tree for the same string. So we call this as an ambiguous grammar. If we have more than one derivation, so we call it as ambiguous. Grammar is called as ambiguous grammar. That is, context free grammar is ambiguous if there is a string W which belongs to L of G, that is two different derivations or two leftmost derivations. Here we have two different derivation trees gives two different leftmost derivation and vice versa. This is said to be ambiguous grammar. This is the ambiguous grammar. We have seen it. Next we will see one more example for ambiguous grammar. If statement. This is example for if then else. If we have if statement, then if expression, then statement. Expression is a variable and statement is also a variable. If and then are the keyword, we consider it as a terminals. Here we have if statement which is replaced by if expression then statement, or if expression then statement else statement. In first we have simple if then. In second production we have if then else. Expression, statement or variables, else is called as terminus. Here we have to derive the string if expression then, if expression 2 then statement 1 else statement 2. That is, if both the expressions are true, it executes statement 1. If expression 2 fails, it executes statement 2. Okay, so we have derivation tree here. First we have to replace if statement by first production, that is if expression then statement. Again this statement has to be replaced by using second production, that is if expression 2 that then statement 1 else statement 2, that is if then else. This is first one, and next one is if statement can be replaced by second production, that is if expression then statement else statement 2, that is if then else. This statement can be again replaced by if expression then statement, that is by production 1. So we have two derivation trees for the same string. So this grammar is also called as ambiguous grammar. Now we will see how to remove this ambiguity. Two different derivation trees may cause problems in some applications which use the derivation tree. String has to be derived using two conditions. The expressions has to be evaluated based on precedence and based on associativity. Here we have what is ambiguous grammar and what is unambiguous grammar. The difference between ambiguous and unambiguous. Ambiguous grammar exists more than one leftmost derivation or rightmost derivation for a string, whereas unambiguous grammar has only one or unique leftmost derivation and rightmost derivation. Ambiguous grammar have leftmost derivation and rightmost derivation represents different parse tree. In unambiguous grammar, leftmost derivation and rightmost derivation represent same parse tree. Ambiguous grammar have more than one parse tree for a string, whereas unambiguous grammar have unique parse tree. This is the difference between ambiguous grammar and unambiguous grammar. So here we have seen few examples for ambiguous grammar. This ambiguity has to be removed by evaluating the expression based on precedence and associativity. Here we have seen what is context-free grammar and how to derive the string and how to derive the string using pictorial representation, that is by using derivation tree, and we have seen ambiguity and how to remove ambiguity. Thank you.